Welcome to my talk, taking a deeper look at the inverse compositional algorithm. This work is done as an internship project in Autonomous Vision Group MPI and also collaborate with Georgia Tech. The seminar Lucas-Canati method is a widely used image registration tool in computer vision. It recovers the motion transform by minimizing the photometric error of the warped image to the template. One classical solution to the Lucas-Canati objective is the inverse compositional algorithm. In each iteration, given the residual of the template to the warped image, it solves the incremental transformation of the origin perturbed template to the warped image, and it updates the warping with inverse composition iteratively. We often use a weight matrix to cope with the influence of the outliers. We also often add a damping term as regularization to cope with the bad initialization. Despite being popular, the inverse compositional algorithm suffers from a number of important limitations. The objective assumes photometric consistency, which may not hold in practice. The high-frequency noises or textures may fail the linearization step and makes the resulting Jacobian less informative. The weight matrix is derived from the classical robust MS meter. In this formulation, the weight of the datum depends on the point residual, which, however, cannot address the context in the residual with high-order information. Adding proper regularization is also a non-trivial task. One common way is to use a heuristic rule to adjust the value damping using the trust region method, but this heuristic rule may not find an optimal solution. In this work, we will take a deeper look at the inverse compositional algorithm and see how we can address these challenges through learning. First, we propose a two-view feature encoder, which learns the feature space for the residual evaluation. The learned feature also makes the resulting Jacobian more informative. Second, we propose a convolutional MS meter to learn the weight matrix using both views of features. The learned MS meter can more effectively leverage the context and the high-order information to weight the samples. Third, we propose a trust region network to more accurately and effectively approximating the trust region using learning. We will use the learned damping parameter to replace the classical heuristic damping in the Levenberg-Marquardt formulation. To summarize, we make three contributions, with each as a learnable module, and we follow the same computational graph as the classical inverse compositional methods. We propose a two-view feature encoder to replace the photometric residual, a convolutional MS meter to replace the traditional MS meter, and a trust region network to learn better damping regularization. All operations are differentiable, and we train all the modules end-to-end using ground truth motion transform. Like the classical inverse compositional algorithm, we also perform our method cost to find. It makes the algorithm more efficient in the computation, and it also helps you learn the features with a bigger receptive field. We first evaluate our method in the 3D object motion estimation using a synthetic dataset we rendered. On the unseen objects with random motions, our method, highlighted in the color green, achieves the lowest alignment error compared to the both long learning and learning baselines. We further evaluate our method on the task of visual odometry using RGBD tomb datasets. Compared to the RGBD visual odometry baseline, which uses the classical Lucas-Canati algorithm, our method performs significantly better in the various testing trajectories under different motion magnitudes. Our method is not only accurate, but also small and fast. Compared to a baseline algorithm using a convolutional network to regress the pose iteratively, our network uses orders of magnitude fewer parameters, but can still achieve faster inference on a commodity GPU. In this work, we have taken a deeper look at the inverse compositional algorithm by reformulating it with three learnable modules. Our proposed solution is learnable, accurate, small, and fast in the inference. Thank you for attending our talk. Please check out poster at 136 and welcome to ask questions.